Okay, so hi everybody. Welcome to the workshop of the Traditional Machine Learning Club. Today, specifically, we're going to focus on PySpark and Docker. My name is Gaston.
I'm Gorg.
I'm Pushpal. I'm Hanley.
I'm Nick.
I'm Phil.
And I'm Jason.
Okay.
We are the Machine Learning Club committee.
So our agenda for today is going to be a brief overview on the basics of machine learning, some of the motivation for this workshop, and then an overview of Docker and PySpark.
So I'll be talking about the basics of machine learning. And we'll do that by broadly defining something we call the machine learning lifecycle. And so the machine learning lifecycle has 5 steps to it. And these steps are essentially going to be placed in order of how they should be approached. So these steps are, first you're going to define your problem. And then you're going to analyze data. So you're going to have some data that you collect and you want to analyze it. And then third, you're going to have a model that you're going to select and use to do whatever prediction you want from your data. And then you're going to validate your results that you get from your model. And then you're going to document your model and the related things, and then try to improve on the accuracy of the model. And so this broadly applies to a lot of machine learning problems, as well as deep learning problems, as well as reinforcement learning problems, just broadly like how is a machine learning problem broken down into different steps and iterated on. So the first part we're going to talk about is defining the problem. So to define a machine learning problem, you need to first do 2 things. You need to figure out the topic that you want your base problem to be on. And so using kind of this topic, you want to figure out what type of output you want and what type of data you're going to use. So an example of that would be if you had a bunch of data about cats and dogs, the potential output you would get from that is doing an image classification network that would allow you to predict whether it's cat or dog inside of the network or inside of the image. So once you kind of have those two ideas figured out, them being what type of output you're looking for, what type of data you have, now you're ready to move on to gathering data. Also, feel free to interrupt me with any questions if you have. Great. So second step is to analyze the data. So now you have an idea of what kind of data you are going to need. So the first step is to gather the data. So you need to put together large amounts of data. Generally, the more data, the better. So this data exists in the form of images, tabular data, or time series data, or kind of anything in between. And so if you want to, if you have a problem that you figure out, first step I would do is do a Google search, what kind of data is out there in that problem. So you want to do cats and dogs, do a Google search, cats, dogs, how can I find this? Can I find data about this? Otherwise, if that doesn't work, Google also has a specific data set search engine, so you can look through there. And even if that doesn't happen, if that doesn't give you any kind of good data, then you should start resorting to, okay, I might have to collect my own data. Now, this is an entire process that you have to go through. So doing web scraping and things of that nature. So first step is to gather data. Then once you have your data, you have a bunch of, whether they're features or images, the goal is to take a look at your data. So every good machine learning engineer, scientist, or researcher knows their data very well. This is kind of, the data is like all the tools in your toolbox. So you can't be a good practitioner of whatever without knowing what tools are in your toolbox. So you need to learn your data in and out. And generally the question you're trying to find out is what kind of patterns can my model learn? If you have an idea of what kind of patterns your model can learn, then you will become better at deciding, at kind of figuring out why the model doesn't work or what will help it work, and kind of gaining intuition there. So second step is to inspect your data, very important. And the third step is to pre-process your data. So data in the world comes in a lot of messy formats. So it might have missing values. It might have outliers in the data, or honestly, several other problems. So what's important is that you should pre-process your data because your machine learning model will require clean data. So broadly, your 3 steps for analyzing data are going to be to gather the data. Second step is to inspect your data, and third step is to gather all your. The third step is to analyze all your data. Okay, great. So now you've gone through the first 2 steps. You've defined your problem. You got your data. It's pre-processed, ready to shove it into a model. Okay, so now what model should you use, right? Well, this 100% depends on your problem formulation. So do you have a simple problem? Is it a simple problem that, and by simple, essentially what that question is asking, is the boundary linear boundary? Can the 2 classes be separated linearly? If it's a regression model, is this easy to model with a simple linear model? If not, does it require a more complex model? Perhaps you need to use some kind of deep learning. Perhaps you need to use reinforcement learning. Is your problem a supervised or unsupervised problem? So your model will largely depend on your problem formulation. But also your model choice will also depend on what kind of data you have. So if you have a lot of data, then deep learning is fantastic. If you don't have as much data, traditional machine learning can be effective as well. So in terms of figuring out what model you want to use, there's several kind of considerations that come into that. But once you've selected a model, you're going to kind of stick to that model. And generally, what you want to do from that point in time is start to validate your results. So once you've analyzed your data, selected your model, you're ready to put all your data into your model and try to figure out how good is my model doing. So the main takeaway from this is we want our machine learning models to have high accuracy on data it's never seen before. In other words, we want it to be good at inference time. And what that looks like is, I can draw an analogy. If you are in a class and you are taking, let's say you're taking calculus, and you got a lot of calculus homework, and the homework is preparing you to understand the concepts, and you'll apply this information you understand from the homework onto the test, which has completely different questions on the same topics. Now, you're not going to have the same questions on your homework and the test. So the idea is you want to train the model to be able to get a high accuracy on the test set, or the new data, or on the inference set. So that's generally the point of, and this is called a generalization. This is what we call generalization. So we want our machine learning models to be able to generalize. So what is the solution there? So first of all, obviously you don't want to train your model on all of your data. You want to hold out a certain portion of it, generally about 10 to 30%. And this is kind of data that you're like, okay, I'm going to test my model on these pieces of data and see if it actually gives me the accuracy I want. So I'm going to hold out a test set, or I'm going to hold out a test set that's going to serve as my test or my exam for my model. So this means that your data is divided into 3 sets: train set, test set, and validation set. And so your train set is used to kind of train your model or to update your model weights. Your test set is going to be used to test the performance of your model. So how well is your model performing on data it's never seen before? And the validation set is used during the training process to accurately measure performance at points within training. This is more pertinent to kind of problems we're using deep learning, where the model training process takes a long time. So you want to get intermediate performance like information, how well your model's doing, at intermediate points between your model training. Because if you have a model training for 4 hours, you don't want to know 4 hours later your model's not doing well. You want to kind of observe constantly and check in. So that's what your validation set allows you to do. Now, we are using simple machine learning models, so that's not going to take too much of a time. So we only have a train test split, train and test set. So yeah, so that is the first, that is how you validate your results. Moving on, we're going to talk about how to, the final step. And the final step is that you are going to document and improve. So now you've kind of put your data into your model and kind of validated the results. Now you have a accuracy value, right? So now models often have design choices called hyperparameters. And these range differently for different kind of subfields. So it's different for computer vision, NLP, reinforcement learning, traditional machine learning. These are kind of different, but generally these hyperparameters have a strong influence on the performance of your model. So what's important to do here is to save your model, number one. Then you want to document the hyperparameters that model is associated with, and the performance, so how good the accuracy is of that model. And so if you're able to keep track of all of these things, you're going to want to start iterating on these training loops. So you're going to say, okay, now I have this accuracy, but I want to do better. So I'm going to see if I can improve, increase my batch size, or if I can try to use a different algorithm, or perhaps tune a little portion of the model. So kind of saving all of this information and kind of training and documenting will allow you to improve your model over time. So these are the 5 steps to the machine learning cycle, life cycle. Are there any questions on this? Cool. All right. So we can move on.
So this workshop that we're going to be going over, and also the lab that we'll be doing after this presentation, involves using PySpark and Docker. So I'll be explaining what those two are at a high level. So what is PySpark? Well, it's a Python API for using Apache Spark, which is a software that will, actually maybe not software, but like a framework that lets you process big data, huge sets of data. So for example, like Google deals a lot with big data. They have to manage tons and tons of websites for their web search service. Also many businesses, they have lots of data stored, like Facebook, Amazon, all of those companies, they have tons and tons of data that they need to process. Apache Spark is a way that lets you handle all that, and it does it through parallel and batch processing, which means you can multitask and take care of multiple sets of data at once, which is very efficient. Apache Spark is originally written in Scala, and there are many different APIs written to incorporate it into different languages. PySpark is the one that lets you use Python, which in itself is pretty handy because since we're interested in machine learning uses Python a lot, and Python also supports parallelization, which really meshes well with Apache Spark. So this is sort of visual representation of what Spark does. So at the beginning, you have to process your data and transform it, and you create a data frame or employee data set functions to sort of explore your data, and then you send that data into your machine learning model. So you can engineer your features a little bit or tune your parameters in that section over there. And then once you are finished processing your data, you send it into your model for training. And then you can do the whole training loop there, like Gaurav was mentioning. And after that, you will have your finished results, and you can send it out using Spark. So yeah, and then the bottom, you can see the servers. They're you can use multiple servers using Apache Spark to handle your distributed data set. Distributed data set means you've split your data into the different servers, and you know, Spark will help you process all that as a single data set. Okay, so moving on. Now, what is Docker? Well, Docker lets you package and run an application in what's called a container. A container is very similar to a virtual machine, but it's more lightweight and more portable. So what this does, it allows you to run more containers at once as opposed to a virtual machine. So a virtual machine, you know, involves assigning a lot of memory for the virtual machine to utilize, but Docker's containers, you don't have to use as much. So yeah, that lets you use more. So containers are also easily shared with colleagues, which is kind of, you create a Docker image and that you can send it to you know, other people. And once they download it, they can run it through Docker and it'll help them set up the environment. And that's what kind of allows us to easily share what we have in our workshop with all of you guys. So if you guys have Docker set up and you have downloaded our Docker image, you'll be able to set it up very easily. And once you're done, it allows for easy deployment of your application. So if you haven't installed Docker yet, there's a installation link at on this slide. Yeah, and World has posted it on the chat as well. So thanks. So let's move on. Yeah, so this is kind of an image of what Docker looks like. So you have your original machine, so like a computer, right? On top of that, Docker runs, and then it allows you to run a whole bunch of containerized applications, and each of them can multitask and let you do a bunch of stuff. So that's kind of the ideology behind Docker. So each of these applications are a single container, and then you can run a whole bunch of them at once. Any questions so far? Okay, so let's move on.
Hi.
Yes.
Yeah. Hi. So I had a question. So let's say in our application we have installed multiple jars or libraries. So when you containerize it, how would that work?
I'll actually be showing something similar to that a little after this, but the short answer is it's very easy and it's not a problem.
All right. Yeah. No worries. Thank you.
Yeah, we'll be covering that in our workshop too, I think. So good question though. Any others?
I just have something to say. I want to say that Docker is a very popular tool that's being used a lot. And the reason for that I can probably motivate is perhaps you have a Windows machine and you need to download or use software that only works on Mac or vice versa. Then Docker will allow you to use softwares that are OS dependent because it allows you to containerize your operating system and kind of launch it in this containerized fashion. And that kind of flexibility is kind of the silver lining of Docker and why it's so popular.
Cool. All right, thanks, Gaurav. I guess we can move on. So now, why do we need to use them? So basically, we'll be using both Docker and PySpark together, and that'll allow us to do some really cool things. So machine learning often involves processing huge amounts of data. Maybe not so much in the workshops that we've done in the club so far, but in the real world, you know, we have to handle lots and lots of data at once to ensure proper training happens. So PySpark lets us handle that big data, and Docker lets us package our model into containers, which lets us, you know, either spread it with others or try and multitask amongst multiple machines. So we can handle lots of different parallelized processes, which can help greatly speed up the time it takes to train a model. And like Gaston and Gaurav mentioned, it's easy to install the necessary dependencies and scale up your model to larger problems. So let's move on to the next slide. So this is an example of using Docker with Spark. You have your Spark running, which answers to the Spark cluster. The cluster is kind of like, not sure how to really explain it. It's just like a hive mind of the things running your application in the background. It processes the big data, and you combine that with Docker, and Docker will work with the distributed file system to run your application using Spark. Yeah, that's MapReduce. That's easy MapReduce. I don't think we're gonna really cover that, so you can kind of ignore that. But that's kind of what how Spark and Docker sort of work together. Okay.
Okay. Before I get started, does anyone have any questions on like the very high level understanding before we get into specifics? Give you guys 30 seconds. All right. Well, let's get started then. So the basics of Docker. So there's three very important concepts that you need to know when you use Docker. The first one is an image. The image is a snapshot essentially of an OS and an underlying file system. It's kind of like a virtual machine, and it's used to make containers. So if you're familiar with like Java, an image is kind of like a class, and you need to make an instance of a class before you can use it. And that's the instance is basically what the container is. It's just an instance of a Docker image that we can interact with. You can run it, you can stop it, you can add stuff. It's very easy to mold. The image that we get it from is just sort of the baseline. And then finally, the Docker file, it's a short script that has commands that are going to be used when you make a Docker image. It's very, very important, and it's how I imagine almost every single custom Docker image is made, is with the Docker file. So what is a Docker file? Well, you can see over here, we have a sample Docker file on the right. It's saying from Python 3, add myscript.py / run pip install pystretch, and cmd python myscript.py in these little brackets. So let's go over what that means. So from, very important, it's always the first line is what image do we want to use as the base for our Docker image. Add is lets you add a file from a working directory to an image, but add's a little overloaded, and they came out with this better version that's simpler to use called copy. So you should always use copy. And then we have run, which lets you run commands on the command line or terminal inside your image. So usually this is for when you need to like make directories or install stuff, that type of thing. And then command or CMD, this lets you set up the command that is used when the image is ran or when you like start or stop a container. And there's many, many, many more commands that are all caps. And I have a link here to the Docker documentation that has all of them in great detail. So why don't I go clone this Git, and then I will.
So right now, what Gaston is showing is setup of our actual workshop right now. So if you want to follow along, you're more than welcome.
So let's open this with code, and we can see what's happening. So we're going to be using Jupyter PySpark Notebook as our base, and we're going to install Pandas profiling. The person who asked about the jar, copy is how you get files into the image. So for example, I'm saying copy, set the owner of this file to this user ID, copy this file, Titanic PySpark.ipy pynb, and put it in this location.
Can you zoom
link to
in,
these
Gaston,
files?
please?
Oh yeah, I can link this in chat. Everything's on the GitHub right here. Okay, let's go back. So I'm merely copying these files and then I'm exposing this port so that when we run it, we can hook up, we can access this particular port. So now that we have an idea of, oh no, I can't zoom in. So let's, so before I show you how to use the Docker file, let's go over some of the steps that might be relevant. So I compiled sort of a cheat sheet in the form of helpful commands. Docker image ls lets you look at all of the images you have installed. Docker container ls with the all tag lets you look at all the containers. And then if you remove the all tag, then you'll only see the running containers. The most important one that I'll be showing you a little after this is Docker build. This will create the Docker image with the specified image name if you run this command in the working directory with the Docker file in it. And then Docker pull is very similar to git pull, and it lets you pull images from the cloud. And then remove lets you remove an image. And if you want to remove an image, you need to have all containers that are based on that image deleted first. And then Docker exec is very cool. If you have a container that's running, and let's say it's running Jupyter Notebook, and that's taking up the, once you have Jupyter Notebook running, you can no longer type on that window. Docker exec will let you open a new bash window so you can continue to type while Jupyter is running. So, and it's not limited to bash, it can be anything. It lets you exec pretty much any program inside of the image. Very sick. Then we have remove for containers, remove container. This one's very long and complicated. So essentially we're saying we're trying to run this image in interactive mode. Interactive as in we can see the terminal that the underlying image is using, and we're trying to connect the port we expose. So in this case, it's 8,888, and we want to expose that port to port 8,888 on our host machine. And then the name here is just what we want to name the container. It makes it easier to start and stop image containers because Docker names them these really long kind of random names. And then image name is just the image you're basing it off of. And then Docker start, interactive mode, container, and stop container name. Then we have Docker commit, which lets you create a new image from the container. So let's say you had an image that you run a container from an image, and like in our case, we're running a Jupyter notebook, and we want to save that Jupyter notebook and share it with everybody. So all we have to do is stop our Docker container after saving it, and then we just commit the name of the container to a new image. And then Docker push will let us push it to the cloud. So with that in mind, let me show you how to do that. So CD. Okay, so
I had a question.
yes.
Yeah, could you please remind me again about which port is, I mean, 8888 port, because both of them are the same number.
Yes, so the port number is arbitrary, but to make the semantics easier, we want to bind it to the same port as on the host machine. So like if you're running, let's say, localhost 4000, some web app, you want to be able to access it from the host machine on the same port. And the reason you need to specify it is because otherwise Docker binds it to some random port, and it's a pain to find unless you specify it yourself. Does that answer your question?
Yes. So the first 8888 port is the local machine port, and the second port would be the port at which the container would listen.
Yes.
All right. Yeah. Thank you.
If you expose the port on stop, will it close the port after the image? Are you talking about on the local host or in the Docker image or container, Vlad?
I guess both, actually.
So
The local host, yes.
you can't access the port on localhost unless you have it available anyway. So that one's sort of always open. But the container, if you remember, let me see if I can open the code again. So here we said we want to expose this, and this means that we're making this this port available whenever we run our container or image. But the only thing that lets us bind the port is in the Docker run or Docker start command. But it's usually just Docker run, and then Docker start remembers the ports that you binded. So
Okay, so
it's
you need
easier
to
to think of it as you're saying, when I run this container, it's going to be using this port. And then when I stop the container, it is no longer using this port.
okay, but it's opened, or the port has to be opened before.
Yeah, on the image, it's always open when it's running.
Okay,
It's just not accessible to the outside world unless you bind it or let Docker bind it for you, which you should never do.
I see. Thank you.
Okay, so now we can, so in the README here, I put a bunch of commands. So we're going to be building our Docker image. So let me just copy this and paste it, and then we'll see that our image is built successfully. And then we're going to run it. So now I can just copy this, and I can access everything on that image that I put there. So please stop, close this. So now I want to stop it. So I simply have to say Control C, and I'll just say Docker stop py. If you don't want to remember all of these commands, the Docker desktop, fantastic utility. It'll let you see all of your images and which ones are in use or running, and all your containers and whether they're in use or running, and you can do a bunch of cool stuff from here. So it's a nice little shortcut. So with that, let me go back to the presentation, and I believe, yeah, okay. So before we move on, does anyone have any questions on Docker? Because this is the time to ask it. Or was my explanation sufficient? All right, well, if nobody has any questions, then I will move on and pass it over to the rest of my group.
All right, so now let's go over Spark basics. Before we jump into Spark basics, I want to remind you what Jason said earlier in the slides about how Apache Spark lets you efficiently process huge sets of data using parallel and batch processing. Okay, so when looking at Spark, there are four concepts we need to go over. Spark context, RDD, transformations, and actions. There are a few things that we need to understand before diving into what Spark context is. Okay, so we have local file system, distributed file system, clusters, and nodes. So let's work backwards. Well, starting off with nodes. Nodes are like, I'd say, mini computers that each have a defined function and purpose. These nodes are also called worker nodes. And clusters contain multiple nodes. And so basically each node is a worker with a specific function or purpose, and a group of those is called a cluster. Moving on to distributed file system. Spark uses a distributed file system so that the data can be distributed to multiple nodes in a cluster. And the local file system is kind of just there to save and load stuff into the distributed file system. So that's basically how the data flows. Goes from local file system, distributed file system, to clusters and nodes. So here, Spark context is the purple arrow that I've highlighted. It's basically the gateway into the Spark ecosystem, or simply a connection from the distributed file system into the clusters and nodes. So when we run a Spark application, what happens is a driver program starts, which is the main function. and Spark context gets initiated. The driver program then runs the operations inside the executors on the worker nodes. So now let's look at the diagram. You can kind of get the basic idea of how everything flows, but I want to clarify what Pi4j is there. So that's basically it allows Python programs running in a Python interpreter to access Java objects in a Java virtual machine. So that's why it's labeled light blue. And you can see how the cluster works with the Spark worker nodes being connected to each other as well. That's it for Spark context. Let's move on to RDD.
Hi, so another Spark basic we should know is what RDDs are. So RDD stands for Resilient Distributed Dataset, and it's essentially the building block of Spark. So these are pretty much elements that run and operates on multiple nodes. You can kind of look at our visual at the bottom. We have our RDDs. So these are pretty much like the data sets. And so RDDs deal with distributed processing and how to manage and transform that data. So this is where Spark does most of the handling regarding transformation and managing data lineage. And so there are a couple operations we can use in RDDs, and they are transformations and actions, which are actually on the next slide.
Yeah. So, okay, before I get into what transformations and actions are, we need to understand that RDDs are immutable. You can't change or undo an RDD once you perform a certain action or activity on it. All right, so transformations, basically doing these activities or actions on an RDD creates a new RDD. And that basically transforms an old RDD into a new RDD. So an example would be applying the filter or map activity on an RDD. And okay, next up, actions. Actions are operations applied on an RDD. They instruct Spark to perform computation and send results back to the driver. So let me just go over real quick what filter and map are. Filter returns a new RDD after applying it on a source database, and the map function applies transformation function on the dataset and returns the same number of elements in the distributed dataset. So real quick, really briefly, I don't think you need to know this for today's lab activity. But there are two types of transformations. One's called narrow, and then we have wider. Yeah, narrow basically computes data on a single partition. There are multiple partitions in a single RDD, and wider computes data across partitions. Yeah, so the main difference between transformations and actions is that transformations returns a new RDD, and actions send back a result to the driver. Yeah, let's look for this slide.
So the other important thing to know is about SQL and data frames, since I think we'll be using SQL and machine learning modules in the lab portion. So a data frame is a distributed collection of rows under named columns, and Spark SQL is Apache Spark's module to work with structured data. So Spark Session is one of examples of classes that we can use, and SQL is the module. So essentially, Spark Session is the mid-entry point that will enable us to program with Spark program in Spark with data frame SQL functionality. And at the bottom, I provided some links. We have the PySpark documentation and also a small cheat sheet for using the SQL module. And I think we're gonna be going over this in more detail later on in the project part.
Great, thank you. That is the end of our presentation today. Are there any questions about all of the things, whether it's Docker, PySpark, overall machine learning lifecycle, anything? Great. So at this point, I think a good thing to do would be to begin by installing Docker. Does everyone have Docker on their local computers? If you already have installed it, could you just put up a thumbs up on the what is it called, the participant stuff? If you already have installed it. And if you're not installing it, you could also just put like no or whatever. If you don't respond, then I'm assuming that you're still working on installing.
And if you're having trouble, you can also let us know in the chat. We had some difficulties when we first started to install it as a group, so it's not very unusual for it to go wrong.
Cool. So I think we can give people about like 5-10ish minutes to keep installing. And in the meantime, if you have any questions, you can speak up or just message in the chat.
Thank you, Castellan. And if I can't install it, that's fine. I'll just watch.
Cool. Yeah, you're welcome to watch, but it would serve to be useful to have the Docker on your computer. Cool. I think we can give people about 2 more minutes to install. Okay, cool. So does anyone need more time to install? Anyone trying to install it and still needs more
Are we
time?
installing Docker or? Okay,
Docker, yeah.
I'm building the PySpark image.
Okay, it's pulling the PySpark image. Cool. So you got Docker installed. Anyone else need time to install
Hey
Docker?
Tristan, so there's some workarounds, but all of them involve you installing it on your C drive first and then using some PowerShell commands to make it move to another drive. So I think, unfortunately, you have to just clear up your C drive and then make it point to somewhere on your other drive for the image directories.
Okay, so I'm going to operate under the assumption that those who want to follow along have Docker installed. Okay, so next up, like Gaston indicated prior, you're going to do git clone of this in your terminal. So I already have it cloned, so I'm in the directory. And then when you have everything cloned, you're going to build the Docker file. Sorry, you're going to run the Docker image. You're going to build the Docker container by running this command. Docker build -t PySpark v2 dot. So if you want to make you'll see that I do not, hold up, Docker containers. Okay, cool, so I'm gonna build it. So I'm gonna do a build.
You need the sudo, Gorov, because you're on Linux.
Yeah.
Unfortunately.
Okay, cool. So I did a sudo Docker build. The sudo is just because my computer is weird. You might not need it. But essentially it's gonna pull from the Docker Hub, install everything. And then what you're gonna do is do a Docker run it. Oh, I need my sudo. Docker run it -p. It is just saying it's interactive. You're gonna set up your port forwarding, and then set up a name. So I'm gonna say tutorial PySpark v2.
You might have a
Okay.
container already running that's using that port. I checked Docker desktop really fast.
Say that again. Oh, I don't have Docker desktop, so I'm gonna just run one that's already working.
No, it's saying that you already are using that socket or port.
Oh, I see.
So just try looking at your containers and then stopping them.
Yeah, there's a command that I have to. Okay. Docker container. Plus, I don't have any containers running.
It says you do. Oh wait, no, it doesn't.
Give me 1 sec. I'm gonna debug something.
Do you have anything else running, perhaps?
I think so. Give me 1 sec.
Oh, and while he's working on that, I'm just gonna quickly plug Docker for regular program use because you can have everything in like a Git repo, and then all you need to do is send the container to your friends or whoever's in your team. Then all they have to do is build the image, and that you can specify in your Docker file that it needs to pull from a Git repo, and then install everything, and then you're good to go. You don't need to worry about Do I have to have these dependencies installed or anything like that? It'll work perfectly. Unless you make a mistake in the Docker file, in which case it won't work at all.
Okay, yeah. So actually, like I want to kind of build off of that point that Gasso was making. Generally, if you have any kind of code that you put onto GitHub, you would want to put a Docker file onto it and kind of allow people to use Docker to launch your code through Docker. Because setting up dependencies and all that stuff is a big mess. So being able to ship out your code in a containerized fashion allows people to use your code, and that's kind of generally the endpoint. Yeah, so now I'm going to do a sudo run. Oh, sweet. Okay, cool. So I'm going to do a sudo run, and I have my Jupyter Notebook running at this address. So I'm going to go ahead and open that up. And if I go inside work, I have the images folder. I have the Titanic PySpark.ipynb, and then I have the Titanic CSV, which contains all our data. So Titanic CSV, we could take a look at it. It's just going to be a bunch of information about the Titanic, about the passengers that were aboard the Titanic the day it hit the iceberg. And so yeah, so now we're going to launch our notebook. And I am going to give it away to Phil. I think, Phil, you're going to take the first part.
Okay. So one of the first, so one of the, as was discussed earlier, one of the first steps is, and one of the biggest steps is cleaning up data and managing data. And visualizing the data is very helpful for doing that. In the step that is being shown right now, there's a pandas profiling. And what's happened is that because there's so much machine learning going on kind of in the world, people have made these wonderful modules that you can import and run, and they'll show and they'll look at your data, and they'll do simple statistical descriptions of it, which we see a little bit lower here. But they'll also do plotting and graphical descriptions of it, and kind of which we'll see when we look at the pandas profiling part. So if we could go down a little bit, run some, we're importing the Spark session and the classification with logistic regression. I didn't really focus on those things, but if we're going to do this, explore the data step here, and we're going to pull it into pandas data frames, which are structured kind of like CSV files that we can perform Python operations on. We can look at the schema, which shows the different columns or how they're organized. Passenger ID, survived. We're looking at the Titanic database of passengers, how old they were, where what kind of ticket they bought, the cabin they were in, was it first class, second class, third class. And so what we're doing is we've imported that data into a data frame from a CSV file, a comma-separated variable file, and now we can start exploring it. Now, so the schema was shown above, and if we just want to look at the columns for the different data types, there's this data frame.columns operation that lets us see it. It turns out that I guess PySpark has its own data frame, and Pandas has a data frame. So these different Python modules have their own version of data frame. So you can see in this next cell that there's a data frame to Pandas, so that we can do Pandas operations on it. And so then here's a view of the top five entries. And And so this is how we begin becoming acquainted with the data. We're going to have to clean up the data. We might want to do dimensionality reduction. We're going to want to find out what's correlated, remove remove correlated data sets, find out which ones are, so this shows us the different object types as they've been imported in by Python into the data, kind of data frames, of each of the columns, each of the data categories that we're using. You can see most of them are integer objects, but there's going to be some that are basically strings or other things. So this operation here, Titanic_df.describe. So we say, okay, we want to describe with statistical, descriptors, the data set that we have. And so you can see this is a wonderful summary way to look at it. We say for each column, for each data type, we can say how many are there. That's the count. What's the mean value? And the mean value doesn't always make sense. It depends on what data type it is. But what's the standard deviation, the min, the max, the first quartile value, the median value is at, I guess, 50%. So that the first one was the mean, the median, I guess that's the third quartile, the 75%, the max. So it gives us an overview of data types that we'll be working with. But one of the questions we're going to have is, if we have a whole bunch of data types, if our data set is very, as we saw above, there's a lot of different categories, we might not want to use all of them. So you can see in the after doing some data kind of discovery and looking at it, and perhaps more analysis, we say, okay, we want to get rid of the passenger ID. We don't think that's going to be correlated with any kind of prediction we're going to do. Maybe we want to get rid of the ticket price. You can see in the note, drop passenger ID, cabin ticket. So we say, okay, we're going to select from that data frame these columns or these types of data, and then we're going to drop the other ones, and we're going to turn it into a pandas data frame, because the pandas module has a bunch of wonderful mathematical operations. And then we're going to explore a little bit more. One way we could run that. So we've done kind of a cull of a more complex data set to a simpler one that we think will be more useful for our purposes. And then what we might want to do is we say, these kind of text descriptors or these statistical descriptors in text are wonderful, but we really like to see more visual representations of data. Sometimes it can give us better insight into how data is distributed. So these are just some examples of some simple plotting tools we have. For example, in here using matplotlib, which is a great module for Python visualization. We've taken the three classes of three first class, second class, third class, three categories of fare that people might buy, and plotted them with respect to data. Because what we might find out if we're trying to predict who's going to survive, I mean, what are the qualities or the kind of vectors of qualities of people who survive versus those who don't. We might say, hey, we think maybe the first class passengers might survive more because the first class is on the upper deck and they're more wealthy, they might have more influence. But let's look at who's in first class. And so this plots the age of the first class is in blue, and we can see the median value, it's kind of around 40, and it shows who's in second class, who's in first class. And using these kind of plotting where we just look at different categories, it helps us maybe understand the kind of relationships that we're going to want to train on. If we look a little further, if we go down a little bit more, there's this is what I was talking about before, the pandas profiling report. So this is for a deeper visual dive into the data, and so you can see on the right hand side in this little kind of box, there's a scroll bar, and if you go up and down, there's all these different kind of little analyses of the data. So for example, if we go back to the top one, if we scroll the bar up all the way to the top, in the overview one, you see there's a warnings button. If you click on the warnings button, you can say, hey, this there are this many duplicate rows still in your data set. You might want to get rid of them. Look at the SIB-SP, that column has 65.9% zero. Does that mean there are no siblings, or does that mean that you don't want to use that data when you try and train it to find patterns? So, but if we go down, for every column, we can see that there's ones that are just binary 0 or 1. We can see they're plotted the relative amount of each one. So, and then we can keep going down, and we can see histograms of age, for categories where there's a lot of values, like the ages of the passenger, we can see histograms. So this is a wonderful way to get insight into the data set that you're going to be operating on. Additionally, in this interactions here, it doesn't look very good in this data set, but for example, you see there's 2 rows here, and you can do kind of, I think they're called scatter plots. So, age versus fair here. Or you could pick age versus siblings, or one of the other ones. And so you have this very nice visual representation of, you can look for correlations, you can look for trends or patterns in the different categories of data you have. And it's really, you just pull it in with a single line. And if we go down more, in terms of a more sophisticated correlation measurement, you can see that this plot here, this heat map, which is showing how each data type is correlated with each other one, is done by, if along the top, there's different measurements of correlation. There's Pearson, Spearman. So instead of having to, if you want to get insight, and depending upon how sophisticated you are, in terms of understanding correlations, you can this just gives you the results in a nice visual, intuitive way of how the data is related to each other, prior to you asking the machine learning tools to find out how the data is related, right? And I think that's, what else is down there? I forget what's below that. Oh, and so there's just some more discussion of, representation of your data. So that's just a nice tool, that the kind of nice tool that, because machine learning is so popular, that people are developing and are available. So perhaps someone else should talk about the vector assembler string indexer.
Cool. Yeah. Thanks, Bill. Can you guys hear me?
Yep.
Yeah. All right. So before we jump into the next part, let's just remember that what we're doing here is that we're trying to look at the passenger data, and in relation to whether they died or they survived. And so how we do that with Spark, we're going to be going over with vector assembler, string indexer, etc. And so before we actually jump into the actual machine learning algorithm, we have to convert the Spark data frame into a data frame that we can use to run through that algorithm. And so how we do that is through something called transformers. And so here it says transformers convert one data frame to another, oftentimes appending or combining columns. And so the features or the transformers that we're going to be looking at, vector assembler, string indexer, vector indexer, and one-hot encoder, these are called feature transformers because they transform specific features in the data frame instead of the whole data frame itself. Cool. And so I'm just going to go over real quick what each of these are. I'll give a more in-depth explanation as we run through the code later. But so basically, a vector assembler combines a given list of columns into one single vector. And so it's often used to combine raw features and features generated by other transformers into one feature vector. And so moving on, string indexer. So it takes a string column of labels and then basically, converts it into a column of label indices. Vector indexer takes an input column in vector form and decides which values are categorical and changes those values to indices. So very similar to string indexer, except it takes in vectors instead of strings. And so this is used often for decision trees and tree ensembles. And then one hot encoder maps a categorical feature represented as a label index to a binary vector. And so each binary entry in that vector indicates the presence of a certain feature value out of all the categorical features. Okay, so moving on to the code. So we're importing all these transformers, and then, so what we're gonna do, we're gonna basically format the sex column into sex index. And so I believe the given sex column has male or female. And so basically what it'll do is it'll, with string indexer, it'll go through that column we're looking at, and then it'll label each entry. So each entry should have M or F, and then it'll label it with the corresponding index just, based on how common that string is. So like M would, if male were the most popular, I can't really see here. Yeah, so for example, if male were the most popular one or like the most common, then it would label a 0, and then female would be 1. And so for every single entry, every single passenger, it would have an additional column with 1 or 0, depending on male or female. Cool. And then with one hot encoder, what we do is we take the sex index column, and so that's the that was created by string indexer, and then basically what we do is we are splitting that into 2 columns based on the male and female sex that we're given, and basically if the passenger is a male, we mark it as I think 1, and then if they're not male, then we mark it as 0. And so we have a column for male and a column for female, and basically we're marking whether it's true that they're male or it's true that they're female. So that's what that does. Yeah, and then so we do the same thing with embarked in the next cell as we did with gender. And then moving on to vector assembler. So we said earlier that it combines a given list of columns into one single vector. And so here we are combining the p-class, sex vector, age, etc., into one single column of features. And so that features column is going to be a vector. Cool. So moving on.
Actually, I just wanted to pause. Does anyone have any questions about the vector assembler, indexer, one hot encoder, and the pre-processing stuff we just did?
What exactly does the dimensionality of the vector output by the vector assembler look like? Is it literally just like one vector with all of the input columns for every
Yeah, so it'd be
row?
1, 2, 3, 4, 5, 6. So it'd be a 1 by 6 vector, or it's 1 by 7 vector.
Oh, so basically just transposes it then?
Yeah.
Okay.
Good question. Any other questions? Cool. All right. We can move on.
Cool. Moving on. So let's introduce the concept of a pipeline. So when we work with machine learning in Spark, how Spark represents the machine learning process is through a pipeline. And so in a pipeline, there are functions called transformers and estimators. And so basically what a pipeline is it links, so we learned what a transformer is earlier. And so it links these transformers with estimators so that we can sort of just run one data frame through the pipeline, and it'll automatically spit out a prediction at the end. And so, yeah, we learned what a transformer is. It converts one data frame to another. And so an estimator is an algorithm that fits or trains the data in some way, producing a model for that data, excuse me. And so our estimator today is the logistic regression algorithm. And yeah, if we take a look at the two diagrams here, basically we're doing the same thing today, except for we're replacing the tokenizer and hashing TF with the gender indexer, gender encoder, embark indexer, embark encoder. And so what we do is, so the first pipeline is our estimator pipeline. And so basically what we're doing is that's where we train our logistic regression algorithm, and just train it to be able to recognize or predict who survived and who died. And so basically we're going to be running our training set through that, and then the output of that will be another pipeline. So it'll be the pipeline model below. And with this pipeline model, you can basically just put any data frame through it, and then it'll automatically spit out predictions. Cool. And so below we are, so we import pipeline, and then we create the logistic regression estimator. And then, so for pipeline, here we're creating our estimator pipeline. And so we're gonna be running all these transformers, so gender indexer, embark indexer, etc. And then we're gonna put it through our logistic regression algorithm. So that's just setting up the pipeline. And then, so now we split our data up into train and test set. And then moving on. So right here with fit model, this is where we basically, so we've already set up the pipeline, right? And so now we are basically running the data frame, the training data frame through this pipeline in order for our logistic regression algorithm to build the model. And so we do that with the fit function. And so, so now we've created the fit model, which is a transformer pipeline. And so it's already fitted, like our data's fitted to the model. And so now we can run our test set through the fit model with the transform function. And so that'll spit out our results. And then, so below here, we're taking a look at the predictions versus if they actually survived or not. So there's a couple points that are a little bit off, but I think it says below the accuracy. Somewhere below, maybe in the next section.
Yeah, I think we're going to get to that.
Can you explain what .transform is doing? Is that the actual prediction part?
Yes, that's So with fit model, we already created the pipeline, and that already has, so that, okay, so the fit model part, that's the part that like we build the model, and then when we run the test set through fit model, the transform part, that's just testing our model to see its accuracy.
Yeah, so it's like you can think about pipeline.fit as like your training. So it's not going to do any updates to the weights of the model or the decision boundary. But here, it will update the decision boundary. But for the transform, you can assume that the weights or the boundaries are fixed, and it's just going to be predicting on the test data. So it's kind of like these frozen weights or frozen boundary applied to new data to test the performance. Does that answer your question, Gaston?
Yeah, I'm just used to the syntax from sklearn, I guess.
Cool. Any questions on this? On the pipeline and how you combine all the pre-processing with the model, the random split, fit, train, test, train, results. Great. Okay. Thank you, Nick. Now we're going to continue talking about the results and try to visualize it. So back to Phil.
If we run this cell, I just found a couple of kind of cool from the Seaborn library, ways to start looking at this. I think probably this should be adapted a little bit to also show who survived. It looks like this plot here is showing the predictions of the females in the column for, I guess, is it showing who survived? Am I understanding this correctly? It shows the predictions and then who survived.
Mm-hmm.
I'm not completely sure if this is exactly right, but yeah, maybe. So this is just the same goal we have, which is to take the results and display it visually because we understand things better visually. I was thinking about this one, so I'm not completely sure it's the best example, but it's an example of a kind of plot you can do. And then below, this is the evaluation, I guess, of the 0.847 of the efficacy of the prediction. Is that correct? Where we do the PySpark.ml evaluation. In any case, I think that's our measurement of the success of our training. And then below is just another way to visualize predictions, just another kind of plot to start looking at the data. And probably eventually we'd want to do more of these. But again, it's nice if we can move from sometimes, I mean, there's a place for moving to visual descriptions of results of data and of distribution. And that's about it.
Great, thank you, Phil. And I think I just have some words to kind of wrap this all together. So here you've seen kind of an end-to-end machine learning project using a very simple Hello World dataset, the Titanic dataset, and kind of how it runs through using the technologies we've introduced, Docker and PySpark. Now, I think the power of PySpark is not clear yet, like why use PySpark. And I think that becomes clear when you have several different servers and you have data on several different servers and it's all like very, very distributed and you want to be able to run some kind of machine learning model across these servers and create these nodes and clusters and all these concepts that have been introduced. PySpark enables you to do that at a very large scale. And so for that reason, Docker as well as PySpark are very important technologies in the job market today. So we're happy that we're able to kind of introduce to you some portions of the concepts of these technologies in context of a machine learning project. At this point, we're able to take any questions. Or with that, I think that is the end of our workshop.
The AUC value that was shown in your screen share was different from the AUC value that I got.
Uh-huh.
So I was wondering if this model is deterministic, will always reach, I guess, at least with the same initial condition, would always reach the same results.
So I think, okay, so models are deterministic at test time. So for example, so yeah, they're deterministic at test time. However, when you're training it, you're trained, like the initial weights of your, or the initial parameters of your model are randomly initialized, as well as the ones on my side. So the initial conditions vary, so the training procedure varies, therefore kind of the weights vary. But if you were to kind of use your model on my data, on like this data right on that I have, which is the same, of course, it's going to have the same exact result. So if you have like an 87% and I have an 84, then it's going to stay 87 for you and 84 for me.
In fact, you could both have 87 and they'd probably predict a little bit differently. They vary a lot during training due to many reasons, including but not limited to like different OSs tend to have different implementations for math under the hood, so that could affect it. The random seed, randomly initialized weights, and so on.
Yeah, I think all that is true, but all that is only during training. At test time, these models are deterministic.
Provided you're using the same saved model.
Correct, yes. Good question, Justin. Any other questions?
Is there a lot of code you would add to have this code run on several machines if you wanted to do so?
Pretty sure you would just have to set up Spark. So you would need to set up some clusters and then make sure that your Spark can communicate them. And I think Spark context handles the rest under the hood once you're connected. It's like, for example, I think the way it's set up, the Spark context uses just your computer as its own individual cluster, and then you have the ability to add other clusters.
Yeah, so I think kind of the key component there is you're going to have to create the cluster and create all the nodes. And that's generally where the hard part is. So creating and kind of putting all of that stuff into the context of Spark. But from there, the code that we've shown is pretty much the same.
Nice. Great, thank you.
And actually, a cool thing about this is I believe that PySpark can be extended to use image data as well. So if you have large amounts of image data across different servers, then you could also use that for that context as well. Not sure about reinforcement learning, because I think that depends on some kind of environment. But yeah. Okay. I think, yes. What's up, Tristan?
Yeah, so to continue on that question about whether it's deterministic, so the way I see it, there's sort of like 3 steps. There's the step where you're like setting things up and like splitting the data into training and testing sets and like setting up the neural network with random variables. And then there's the actual training part. And then there's the using the neural network that you've made at the end. Which of those are deterministic again?
Okay, so the only part that is deterministic is the model at test time. So the model at test time, so basically, so let me kind of go back. So when you're splitting your data, that's also not deterministic. That's random splitting. When you're training, you have a random weight initialization. That is also a random starting point. So you can kind of think about it as you have this like landscape of a loss function, right? And so you randomly place yourself at some random point of the loss function. So if you perhaps happen to be right near the minimum, then like you don't have a lot of things to learn in your training. But if you're like in the worst possible starting point, then your training is going to get harder. So that is also random. However, at test time, what happens is you've kind of gone down the landscape and you're at this point. Your model saves that model. Your computer saves that model and runs that exact set of weights to predict new, to have new predictions on new data. And that is deterministic because your weights are fixed. And so that being, since your weights are fixed, it's going to have the same exact prediction for any given piece of data.
Okay, so the place you're initially placed on the loss function is random.
Correct.
But the process of actually going down the loss function, is that deterministic?
You're asking, is the optimization deterministic?
Yeah.
The methods it uses are deterministic in the sense that they're consistent across training sessions, but the numbers are
okay.
random, I guess.
Yeah, so generally I think the optimizer is deterministic, but like you're gonna want to change different parts of the optimizer. So what is the learning rate? Like, do you want a large learning rate or a small learning rate? So these are things that you tune, but I think the optimizer is deterministic as far as I know. I could be wrong on that.
Okay, thanks.
Good question. Any other questions broadly about the workshop, machine learning in general? Cool, great. With that, thank you everyone for taking time out of your Friday afternoon. And thank you for spending your semester with us at MLI HSU. So it's been great. And we've learned a lot. So next week, we will be taking the Friday off because it is Thanksgiving week break. So enjoy your break. The following week, we will have a presentation from the Visual Language Committee, and they will be presenting their progress on their work. So yeah, thank you everyone for taking time. I hope to see you all soon. Enjoy.
Thank you for the workshop, everyone.
Thank you.
Thanks,
Bye.
great workshop.
Yep, thank you.